So when the protostar forms, protostar is going to be cool compared to stars and big. That puts it somewhere in the upper right of the HR diagram. Now, what's going to happen is that if the star is low mass, if the protostar is fairly low mass, Kelvin-Helmholtz contraction will go on for like 1 billion years, and it will gradually be giving off energy and compressing, staying roughly the same temperature, and just drop down to the main sequence. For stars that, on the other hand, are very, very high mass, they're shrinking, but they're getting hotter in order to balance against all the force of gravity, and so they're having to get hotter and hotter and hotter. And so even though they're shrinking, they're getting hotter and hotter and hotter. So they're staying roughly the same brightness and heading off to the HR diagram. Now, for some stars like the Sun, they actually start going down here, Kelvin-Helmholtz contraction, and they jump over and then drop down. And so that jump right there is an interesting sort of thing. The reason it does that, the reason all the stars do what they do, involves heat transport. How does heat get from the inside of the star to the outside? So we got the protostar, it's heating the most in the middle, and you got the heat out to the surface where it radiates off into space. Well, there's basically 3 mechanisms for heat transfer. In physics, we talk about conduction. So you heat one end of something, and the molecules start vibrating and bumping the next molecules and bumping the next molecules until eventually the heat gets to the other end. Okay, basically the more the molecules move, the hotter it is, so that you get heat from one side to the other. Okay, radiation. The molecules are jiggling around, and that's producing electromagnetic waves, and so energy is just carried away that way. And then convection. You heat a gas, it expands, and when it expands, it's less dense than the surroundings, so it rises. Okay, and as it rises, then what happens is that the pressure is released, and so it expands. When it expands, it cools off, and if it cools off to where when it cools off, then gases, when they cool off, they contract, and when it gets denser in the surroundings, it starts sinking. And so hot gas rises and cool gas sinks. And so this is the different mechanisms for heat transport. And so, of course, this happens naturally in the atmosphere. The sun heats the ground, the gas rises and then sinks, and so you get natural convection in the atmosphere. Radiation, you heat something up, you can just put your hand near it and just feel the heat radiating off of it. Conduction, again, heat conducting through material. Now, in stars, what we discover is conduction is pretty much not a major factor. Conduction does not really apply inside of stars. So radiation and convection. So whichever condition works best depends on the circumstances. If gases are really thin, radiation works better, works really well for energy going through. Different conditions that are opaque, radiation doesn't work so well. You also need to get the density and the temperature profile right. If it's all the exact same temperature, then you heat a gas, it expands, it's now warmer than you heat a gas, okay, it expands, it's now less dense than surroundings, and so it rises. But if the gas above it is less dense or less compact, it won't rise. Or if it's warmer above, it won't rise. And so all these conditions, have a huge impact on weather and atmospherics and so forth. But they also have a lot to do inside the stars. When the protostar is first forming, it's pretty much convective all the way through. But for stars that are about the size of the sun, what happens is that when you compact them enough, the inside gets to be in this condition in which it's very, very stratified in temperature. So the temperature drops off too quickly with distance, and the result is that if something expands, it rises, the pressure drops off, and it cools, and now it's cooler in the surroundings, and so it doesn't rise anymore, and so convection quits working. And the only way for heat to get out is radiation. And by radiation, I don't mean it's just shining straight out. You know, what happens is it goes a short distance, bumps into a molecule, bumps, so it's bumping into atoms. And so what happens is it's bumping around between atoms, it's radiating, but it's bouncing around, and it takes tens of thousands of years to get out. In the meantime, that allows the star to warm up. And so that would mean that the star would, on the HR diagram, be going down, and then suddenly start going off this way as it's warming up, then start going down again. And so we call that the Hayashi track, named after a couple of astronomers, Hayashi and Henyey, who calculated how this would behave for protostars. And they calculated the stars that are about the size of the sun and a little bit bigger than the sun and maybe a tiny bit smaller than the sun go through this Hayashi track. And that changes the internal structure of the sun. So the sun has this region in the middle that's radiative, and the outer part is convective. Okay. Stars that are on the Hayashi track that are undergoing all these changes turn out to be slightly unstable, and they're still protostars, but they look like stars, and they're unstable, so they get brighter and dimmer. They start getting magnetically active and having huge flares and pushing some of their outer layers off into space explosively, and that releases energy too. And so these things are variable stars. The very first one discovered doing this is a Tauri star. And so Tauri stars are protostars. They are in the process of forming. Sometimes they'll actually start the process of fusing lithium. So Tauri stars, in there somewhere. Okay. For stars that are less than 0.8 solar masses, they stay convective forever. So they never get that radiative zone in the middle, so they stay convective forever. That actually has a very important impact on how they live and die. We'll get to that later in the summer. Stars between 0.8 solar masses and 4 solar masses, on the other hand, they do what the sun does. They become radiative on the inside and convective on the outside. Stars that are more than 4 solar masses, actually turns out that the temperature profile is such that the outside is radiative and the inside is convective. So they're kind of backwards in there. Okay. But the next question is, what stops the nebular collapse? Like I said, the Kelvin-Helmholtz contraction can keep a star shining for a few million years. And so for a long time, they used to wonder about what made the sun shine. And they said, it's hot and it's bright, and they think, what's hot and bright? Oh yeah, fire. Okay, so they thought the sun was fire. And so, the chariot of Apollo, flaming chariot of Apollo, fire. Okay, so the sun was thought to be fire, but if you go through the math, it doesn't work. The sun is actually only able to burn for a few thousand years. If it was fire. Chemical reactions don't actually work to release more energy than that, and so it only lasts for a few thousand years. Well, we know the sun's been shining more than a few thousand years because we have historical records that go back more than that. So the sun was shining. So the other idea they came up with, Kelvin-Helmholtz contraction, and that would actually work for a few million years. And they thought, well, that goes way back before prehistory, so prehistoric time. So surely that's working, and that was what they thought was making the sun shine. In fact, that idea would normally make stars hot and then gradually cool off. And that's why they used to say that early stars are hot and late stars, late spectral types are cool. In fact, they used to even think about that at the beginning of the 20th century. They thought that the sun used to be warmer and is now cooling off. So they thought that many millions of years ago, for example, Mars was like Earth, and then Venus is like Earth was millions of years ago. It was in this time that they thought, well, life started on Mars first, then on Earth, then on Venus. They were actually thinking maybe Venus had dinosaurs on it, and that intelligent life was on Mars long ago. And then as the sun gradually cools off, then life, is going to change. And so that during this period of time, that's when Herbert George Wells wrote a novel, H.G. Wells, called The War of the Worlds, in which Martians were trying to move from a dying world Mars to Earth. Now we know all that's entirely wrong. The sun does not cool off as it ages, not in that fashion, and so it doesn't work. And of course, dinosaurs tens of millions of years old, and so the sun has to have been shining for that long. In fact, billions of years. And so how do we do that? So there has to be some other energy source that shines, that makes the sun shine. And that energy source is actually what would stop a protostar collapsing. Well, Hans Bethe, who was working on the atomic bomb, also realized that if hydrogen is compressed enough, it will fuse into helium. Now, 4 hydrogens make a helium, but hydrogens weigh 1.008 atomic mass units. Helium weighs 4.003 atomic mass units. So 4 of these weighs more than that. So something else has to give. Some of this extra mass has to go somewhere. Where does the extra mass go? The extra mass becomes energy. So what we know is that millions of tons of the sun are fusing into energy. Hundreds of millions of tons of the sun are fusing into hundreds of millions of tons of helium, but millions of tons are being converted into energy every second, and that's what's making the sun shine. And so that's the process that stops the nuclear fusion. All right, that stops the Kelvin-Helmholtz contraction. When protostars begin fusion, they now are stars, and that is the nuclear fusion, the nuclear reactions inside the sun are really what makes it a star. And so at that point, it will fuse and keep doing that for the rest of its life on the main sequence. And it turns out it can fuse very efficiently. Like I said, the sun can stay what it's doing for over 10 billion years. Far longer than the age of the sun or the earth. So the sun can do this for 10 billion years. How much mass a star starts with determines how quickly it forms. It also determines how much fusion is needed to sustain it against the mass, which determines the temperature. The more mass it has, the more it has to fuse, and the hotter the star is going to be. The less mass it has, less it has to fuse, and so the cooler the star is going to be. And so that gives you where on the main sequence the star ends up. And it starts at a particular spot in the main sequence, what we call the zero-age main sequence. Because it turns out as stars age, they actually wander a little bit around on the HR diagram. But this is what actually triggers the difference between a protostar and a star, is once it starts that nuclear fusion.